guess what? We're doing a DIY. So for a while now, I've been really looking for a special project to do for our next DIY, and really I was having a hard time coming up with something really good. Now our last few DIYs did really good. You guys seem to really love them. And you know what, with this next one, I wanted to go even bigger. So I've really been thinking about this for a while, and I think I got something you guys will really like. So this is what we ended up with. So what we have here is an Injector flow bench. So I decided this is going to be the next DIY project. So for some time now, I've wanted to build one of these and I just needed an excuse to do it. And I think a DIY video would be good as any reason just to do this. So today's video is going to consist of a DIY on building this setup yourself. Now, I'm not going to go over absolutely everything involved with this because while it is a DIY, honestly, I think if anybody's getting to the point where they're deciding that they want to flow test injectors, they probably know the basics to a fuel system. So I'll give a quick description of what we have going on here, but honestly, this is not what the video is about. The video is not really about building what you see here on this bench. It's about building what controls what's on this bench. So just so you guys understand what's going on here, this should look familiar to a lot of you guys. This is a truck fuel rail. So this is the factory truck LS fuel rail off of an early 2000 Silverado, Sierra, Yukon, practically anything that came with a 4.8, 5.3, or 6.0. This is your standard fuel rail. So the reason I use this is, one, we have tons of these, mainly because every time we do a swap, we have one of these left over. Reason number two, this is a return style fuel rail with its own built-in fuel pressure regulator. So everything you need is on this fuel rail. The only thing you're missing is a pump. Easy to obtain. Most of you guys probably already have one of these laying around. All you really need to do is chop off the passenger side of the rail and deadhead it. Just cap it off. Because we're only going to do 4 injectors at a time. Really, that's sufficient. If you look at most flow benches, they do only about 4 injectors at a time. So this should work. If you guys don't have one of these, your local pick and pull. You can go down to your local pick and pull. I think where we go, it's about 15 bucks to pull a fuel rail without injectors. Do yourself a favor though. If you do that, try to see that some of these pigtails for the injectors accidentally fall into your pocket or something. You know, wink, wink, nudge, nudge. That'll make it a lot easier. That way you don't have to like splice together some nightmarish thing to make your injectors fire. This is so much nicer. So like I said, so, you know, grab yourself a fuel rail, chop it in half. You have 99% of this bench done. So this is a 300 liter per hour inline fuel pump. The only reason I'm using this is because I had them. I just had one laying around. If you have something else that's laying around that's capable of flowing about 60 PSI, then you're good to go. You don't need to use anything this large, but the reason I'm using this is less than 30 bucks on eBay. So if you're looking cheap, you can go ahead and use something like this. Otherwise, if you have a fuel pump laying around, use it. So a little hard to see, but if you take a look, our feed coming through here and then back in to the top of the feed rail. Then we have our return rail here, and then we're just returning it back. So we're using some good old-fashioned mineral spirits as a proxy for fuel because of 2 reasons. 1, it don't go boom. Number 2, it actually cleans the injectors in the fuel rail. So works really good. And I can just keep dumping back in here and keep using it. But I do have a fuel filter, just a cheap inline fuel filter, and that's just to keep any debris that might go back in here after we do flow a bunch. Because we're going to try to reuse this a little bit, but we want to keep that from going through the injectors again, because that's kind of going to defeat the purpose. This is essentially our fuel cell, feed and return lines. That's it. That's simple. So other than that, we're just powering it as normal. I'm not going to go too greatly in depth here. If you guys want to see more information on how we do a standalone setup, but we've actually covered everything to hook a fuel pump up to an engine just to start it on a stand. So this is no different. So what we're doing, fuel pump is actually going to be powered off a relay. The only reason we're using a relay in this case, I just don't feel like pulling 15 amps to a small switch. So instead, we're just using that to trigger a relay, which is going to run directly off the power feed that we're going to be feeding this. So just really simple. It's a relay acting like a relay, doing its relay thing, switching on the voltage to the pump. That way I'm not feeling if it decides to short through that button. You feel me? So now we have our injectors and a fuel rail and a fuel pump and our fuel proxy for the flow and a solvent to clean them. So how are we controlling all this? So I got a set of buttons and switches here, and you guys might want to know what they're doing. So I'll give a quick rundown. Power means power. That's exactly what it means. We're going to use this switch here to power the whole system on. So the fuel pump won't start running, but the switch to the relay will finally get 12 volt power. So that way this switch will work to turn the fuel pump on. So this will be our master power on and off. This one is going to go ahead and control the fuel pump. It's going to get its 12-volt source from this power switch. So this one's pretty much turning on power to give this one power and anything else that needs power. But that's when our fuel pump will be able to be activated. And then we have these 3 buttons. What do these 3 buttons do? Well, this one purges. So purge is just going to run all 4 injectors at the exact same time at 50% duty cycle. And it's going to do this for 1,000 milliseconds, or 1 second. It gives me the ability to, well, a couple of things actually. It's going to give me the ability to clean any air out in the lines. If I just started the test and I just put these injectors in the rail and I started the pump up, I'm going to have some air in these lines. You don't want to start flow testing your injectors with one of them just having a big old air pocket in it. You're going to get a bad test result. You're going to have one of them that's going to be far less than the others because it's going to have to purge the air first and then it's going to start flowing. So we can go ahead and purge it. This is going to give us a 50% duty cycle pulse on all 4 injectors for 1 second. And then if I want to press it again, I can press it again, and I can press it again until I see liquid coming out of all 4 injectors. And then we'll go ahead and reset our tubes, get a good baseline for our tests. So that's what our purge button's for. Cycle is going to do exactly that. It's going to cycle. It's going to go through duty cycle. And if you guys know how injectors work, they work by duty cycle. Duty cycle ranges from 0 to 100%. And that's the duration that the injectors are on versus being off. 0% duty cycle, they are off 100% of the time. 100% duty cycle, they are on 100% of the time. So 50% duty cycle, they are on half the time and they are off half the time. That is 50% duty cycle. So when we use a cycle, we're actually going to be cycling. We have these split into 2 banks, so it's not the whole system running all at once. So we have 1 and 3 on bank 1, 2 and 4 on bank 2. That way we're not running all 4 injectors at once trying to pull down. If you don't have a pump, like this pump will be able to support all 4 injectors running at 100% duty cycle all at the same time just fine. If you had a smaller pump, that may not be able to keep up and you might get bad results because of it. So when we press our cycle button, it's going to go through a cycle of duty cycles. It's going to run bank 1 for 2 whole seconds. That's 2,000 milliseconds at 50% duty cycle. Then it's going to stop, and then it's going to activate bank 2 for 2 seconds at 50% duty cycle. We're going to start one, finish one, start the next one, so on and so forth. So we're going to cycle bank 1 to bank 2 through different duty cycles. The way I have mine set up, and you can set yours up as whatever way you want, and I'm going to show you how, but the way I set mine up, we're going to go through the range of duty cycles from 50% duty cycle for 2 seconds, 60% duty cycle for 2 seconds, 75, 85, and then 100. So for 10 seconds, they're going to run through 50 to 100% duty cycle in 2-second increments. That will give us a flow rate of all the injectors through different duty cycles. So we're not just saying 100% on, we're also checking to see how they react throughout the duty cycle range and if they're still flowing correctly. A lot more to know than just wide open, whether or not they're all flowing the same at wide open. That brings us to our last one, flow. This one will run bank 1 for 10 seconds, 10,000 milliseconds at 100% duty cycle. So that means on 100% of the time. So that is going to tell us how much the maximum amount this can flow within a 10-second period of time. Now, that might seem trivial for 10 seconds, but we can throw math at that and figure out what that equates to. In this case, we're measuring milliliters, but we can see what that equates to in pounds per hour. But that's just kind of a simple overview of what we're doing here. So while it may sound scary what we're doing here, here is what it is. This is the heart of what we're running here. This is a programmable logic controller. Now, if you guys know, then you know what it is. If you don't know, then I'm going to ask you, what do you think you would pay for a programmable logic controller that can do all of this, do everything that we want it to do, be able to program through these duty cycle ranges, be able to do all this stuff? What do you think you would pay for this? Because I guarantee if you don't know what it is, then you're probably wrong. These things range between $8 and $20, depending on which model you get. So what we're using here is called the Arduino Uno. This is a very common logic controller. A lot of hobbyists use. It's not a super high-end one, as you can tell from the price, but they work very, very well for a lot of simple projects like this. And they are not hard to use. They're not hard to understand. They're not hard to program. There's a wealth of information out there. There's entire forums communities devoted to these. Believe me, if there's something you want to do with one of these, it's already been done and they've already shared the code for it. It's probably the easiest way for anybody to ever get into coding is to start out with these guys. What we're doing here is we're using an Arduino to be able to control our injectors. So once we turn this master power switch on, we are powering on our Arduino. We're giving power to that switch, like I said, for the fuel pump, but we're also powering on our Arduino. Now that we've covered all that, and if you guys are still awake, I'll try to show you guys how those circuits are laid out on my setup. As you can see, we have the Arduino mounted. So we have our 12 volt positive coming in for switch. We have our ground coming in directly from our power source. On the other side here, we have our 3 button inputs. We have our 2 outputs to the injectors. We have our transistors mounted down here. So this is for bank 1 and this is for bank 2. Resistors are already soldered in line there. I'm controlling my whole build through a benchtop power supply. If you don't have one of these, don't worry, car battery will work. 12 volts is all you need. Mine just gives me the addition of being able to run 5 volts or 3.3, cleaner signal. You don't need it. You could just run a 12 volt battery. As long as your battery is big enough to support this fuel pump pulling on it. At the same time, I'm trying to run the Arduino to make sure that you don't have too much of a voltage drop. These things like that finicky if you introduce too much of a voltage drop to them. And if you do have any issues like that, easiest way, use your barrel jack and just plug it into a wall wart rather than sharing a load with the injectors and the fuel pump. If you're not having issues, you're fine. If you are having issues, just utilize what's already there. Give it its own power source. That way it doesn't have to worry about noise and voltage drop. So now that we've covered most of what's going on with this rig, we're going to go ahead and get into how to actually code it, as well as go over the circuit diagram on how to set this all up. All right, guys, we're going to go ahead and jump right into the coding section. I don't want to make this section too terribly long because we are going to make this code available for you guys to download. And really, I'm just trying to give you a 1,000-foot view of this code so you have a general understanding of what is written in here and why it's written in here. That way, if you're looking to modify the code to suit your needs a little bit better, you'll have a much better understanding of what it is you need to modify. So we're going to go ahead and run through this code real quick. So this should be quite fun. So to start things out, we're going to go ahead and jump all the way to the top. So we're going to look at these first 8 lines of code and kind of let you know what they're being used for. So anything before this void setup is going to be used for essentially declaring things. And in this case, we're declaring the variables that will be used later on in this code. So let's talk about what these words in blue mean. So first, we're going to talk about this int. So what an int is an integer. An integer is a number. So when we're using it, we're going to say that this variable is going to be a number. It's going to be nothing else other than a number. But on these ones, however, we have this const before it. What that means is that's shorthand for constant. And that just means that these variables, these numbers will never change. They're set to a constant, unchangeable number. So because this is representing a static pin number, it won't ever need to change. So we just declare it as a constant integer. And we're doing that for every variable that represents a pin. Down here where that variable can change, we don't want to call it a constant. We just call it an integer because it will represent a number that can change based on a dynamic situation. So the first major section of your code is going to be your void setup. Everything contained within these 2 brackets of your void setup are things that are going to run one time. These are only going to run once the board is powered up for the first time. After that, it is never run again unless the board is reset. So in here, we have what are called our pin modes. And what that does is allows us to set how the pin reads and sends signals. What that means is these pins can either be set to input or output, and you can dictate what type of input output they do. So in this case, we're using what's called an input pull-up. And what that essentially means is that the pin is set to read a pull-up in voltage. A pull-up in voltage means it's going to read a 1 or a 0 based on whether it is pulled up or pulled down. Pulled down means that it is reading 0 volts, or essentially a ground signal. Pull up means that it is reading the top of the 5 volt range that it can read. So everything in between is essentially a null value. It only makes a value of 1 or 0, whether it's reading ground or 12 volt positive. This next section here is specific to pins 3 and 11. So this code in particular will set the frequency of pins 3 and 11. It says 31. It's actually 30.64 to be exact. We do this because these pins have default frequencies. Specifically, pins 3 and 11 are defaulted to a little over 490 Hertz. It's a lot faster than we need these to cycle. When we're setting it to only pins 3 and 11 because those are paired together. So that brings us to our void loop. As opposed to the void setup that runs only one time, loop does exactly what you would think it would do. It's going to run everything within these brackets an infinite amount of times. So it will never stop until it either crashes or you shut the board off. Hopefully if you're doing your code correctly, it's not going to crash. So in here, the first thing you'll see we're defining is our purge, flow cycle, and flow 100. So if you recall back to the control panel, we have purge, cycle, and flow. That's what we're using on these respectively. These are just the variables I originally wrote for them, but that's essentially what they mean. The flow cycle is going to represent cycle. Flow 100 is just the button for flow. So the first thing you're going to notice in red here is the digital read and the variable calling out the individual pins, which are represented as button 1, button 2, and button 3. So what that means is we're going to digitally read those pins, meaning we're going to read the digital signal coming in from those pins. Moving on, this is the meat and potatoes of our code. So what we're looking at is called an if-else statement. It's simply saying if this condition exists, do this. If it does not, that would be your else, do this. So if statements have to have a condition or conditions. You can have multiple conditions. Else statements don't have conditions. Else statements run if the if statements are not true. In this first if statement, we are looking at purge. So if you recall above when I was talking about the 0 versus 1 of the input pull-up, this statement says if purge is equal to 0, meaning that it is a ground signal, we are going to execute this command. If it is equal to anything other than 0, then it will continue down this list until it either finds a condition that is true or reaches its else statement, and then it will just continually loop through this command. So let's look a little bit more into what this if statement is asking. So if this condition is met, it is going to start at the top and work its way through this command. This command structure starts with asking it to do an analog write to bank 1 with a value of 127. What does that mean? So what an analog write is an output for the PWM signal. On the Arduino boards, the PWM signal will be a value of 0 equaling 0% duty cycle, all the way up to 255 being 100% duty cycle. Try not to bore you guys too much, but what a duty cycle is essentially a square wave setting ons and offs. And if you are at 50% duty cycle, for the injector's case, the injector during its 30 pulses a second at this frequency is going to be on half of the time, off half of the time. So essentially you're setting between each cycle this duration of on versus off. The closer we get to 0, it is more off than on, and about 127 and a half, so 127.5, we are actually at 50% duty cycle, meaning that the offs are equal with the ons. That is cycling exactly 50% on and off. The closer we get to 255, you guessed it, it is on most of the time. So if you hit 255, you are on 100% of the time and off 0% of the time. Complete opposite if you're at 0. So that would be the best way to understand what's going on here. So if this condition is met, it is going to set bank 1 to roughly 50% duty cycle. It is going to do the same thing for bank 2. So once these two lines are ran, it is now going to jump to this line. What this delay is doing is setting a delay of 1,000 milliseconds. That is equal to 1 second. So what's going to happen is it's going to execute these two lines, it's going to execute the delay, and then it will stop at this line and not proceed until that delay time has expired. Once that delay time is expired, it will continue down through the bottom of this code, all the way back up to the top, and then it'll check this condition to see if it's true again. By this time, you've already let off the button. So the condition is not met. What is it going to do? It's going to ignore everything after this, and it's just going to jump through to the next if statement. If this condition isn't met, it's not going to read all this. It's just going to jump to the next if statement. So we're not running commands that don't need to be run. So now you kind of generally understand how it runs through the statement. So we'll go down to our next statement here. If flow cycle equals 0. So if the condition of that cycle button has been met that has been pressed, it's going to start running through these series of commands. So as you can see, we're doing something very much similar to the last set of commands, and that is we are running bank 1 at roughly 50% duty cycle. However, we are running bank 2 at 0. It's a very important distinction to make that you set them accordingly. If you don't reset their values, they will continuously run. So specifically here, we are telling bank 1 to run at 50%, bank 2 to run at 0. And then we're telling it to delay that for 2 whole seconds. So it's going to run these two banks at these duty cycles, which essentially is bank 2 is off, for 2 seconds before continuing to the next command. And that is where we set bank 1 to 0 and bank 2 to 127. Like I said, it's a very important distinction to make to, after this delay, set bank 1 back to 0. Otherwise, bank 1 will continuously run at 127 unless told otherwise. You have to remember that if you turn something on, you have to turn it off. So after the 2-second pause, we're going to go ahead and switch banks. And we're going to do that for 2 seconds. And then we continue down. It'll do the same thing now at 60% duty cycle, cycling between both banks at 2 seconds. And then 75% duty cycle. and then 85% duty cycle, and then finally 100% duty cycle. So it's going through all of these duty cycles for exactly 2 seconds per bank. So each bank is going to get a total of 10 seconds of runtime. And don't get too hung up on the percents. I know that they're not equal. I know I kind of jump over here. The reason being is this does not have to be an exact number. Essentially, we're just trying to run it through multiple duty cycles. That way we can measure to see if the flows are the same across the injectors at different duty cycles. Now, finally, we're going to jump down to flow 100. The condition for this is if that flow button is pressed, what are we going to do? We are going to run bank 1 at 100% duty cycle with bank 2 being completely off, and we're going to do that for 10 seconds. That's 10,000 milliseconds. After that delay is elapsed, we are going to switch those banks and then do that again for 10,000 milliseconds. So this is going to give us a full 10 seconds of injector flow on both banks. And once that's complete, we can use the data from this flow test to figure out what the total flow rate of these injectors are. So now you notice that we come up to our conditionless else statement. No conditions, it's just else. If none of these are true, what are we going to do? We're going to set bank 1 and 2 to 0. Now, imagine for a second I didn't have this here. If you didn't have this else statement here, the code will still run. What it won't do is stop running. If no other button is pressed, it's just going to go back to the top of the code and run through again until another button is pressed. And the entire time, it's going to leave this bank at the last state you left it in. So that's why we have our else statement. So that is the broadest level overview I can give you guys of this code. So I hope for the most part that makes sense to you guys, at least enough that if you wanted to modify it, you could figure your way through it. I'm an IT professional by trade, but I am not a professional coder by any means. I have some basic knowledge of a little bit of coding, but for the most part, I'm in the same boat as most of you guys, and it did not take me much time at all to figure out how this code works and how to manipulate it. So I think you guys would be able to handle this just fine. All right, so before we start talking too much about the schematics, I want to quickly go over the parts that we're going to be using within the schematic. So this is the parts list that you will actually need to be able to build this setup, and I'll put links to these in the description below. First and most importantly is going to be our Arduino Uno. You can use any Arduino board you like. The reason I picked the Uno is probably going to be the easiest one for most beginners to work with, being that it does have an onboard power jack. That way, if you're a little more nervous about, micro soldering on these boards, you should be able to terminate most of your buttons with the pins and then just use power off your power jack. So that is just something to keep in mind. So you will need one of these. Here we have the TIP 120 transistors. You will need 2 of these, and these are to control your banks. So if you don't know what a transistor is, it's almost like a very fast solid state relay, except for it only has 3 pins. So really you're only controlling 1 in and out. By the way, with my diagram, this just happens to be the set I purchased. Usually it's base, collector, emitter. The set I got, the emitter ended up being the center pin. But the way this works is your base is your controller. This is the one that's going to be connected to the output of your Arduino. The emitter is going to go to the device you're controlling, and your collector is going to go to ground. You do need to put a resistor between your base and your Arduino output, and that's to protect from back voltage from frying that output. Now, that resistor's value is based on a lot of specific criteria, but I essentially got it down to being around a 470 ohm resistor. That way you guys don't have to worry about trying to figure out the calculations. That brings us to resistors. You will need 2 470 ohm resistors, and those are for your base pins. You will also need 3 10K resistors. We'll talk more about this in a minute, but those 10K resistors are going to be necessary for your input pull-ups. So now we have our relay. So this relay is going to be used to control the fuel pump. So depending on how you have your fuel pump connected, you may not need a relay. But as I stated earlier in the video, it's better to use a relay as a switch when you're controlling the fuel pump rather than the actual switch. That way, if the switch were ever to fail and ground out, it's not going to pull that right through your finger when you're flipping the switch. And then finally, that brings us to our buttons and switches. So you will need 3 momentary buttons and 2 two-position switches. So these will be our 3 momentary push buttons to activate each function of our flow test, and then our 2-position switches to power on the board and power on the fuel pump. So this cluster on the screen before you is my best attempt at creating a schematic. I'm sure I did a bunch of this wrong, but this is truly my first attempt at this. So as you can see, we have our whole setup laid out in front of us, including the board, our injectors, and our fuel pump. So we're going to go ahead and quickly try to go over all the circuits listed here. We won't go over each and every one of them. We're just going to touch on what matters the most. So we'll start with our 12 volt feed and then move on to our ground. So for our 12 volt feed, this is going to be our battery input coming in, or if you have a benchtop power unit, this is going to be your 12 volt feed coming in from that. The first thing that it's going to be running to is uninterrupted circuit directly to the relay for the fuel pump. Now this will go absolutely nowhere until the relay is energized. As you can see that the pump will actually be connected to the normally open portion of the relay until this coil is actually energized. Nothing will actually be sent through there. The second thing we're going to go to is the main power on switch. That's the top switch that we have on the flow bench itself. Once activated, that power switch will send our 12 volt signal to the positive side of all 4 of our injectors, as well as the voltage in pin of our Arduino. So just in case you were wondering, that's what the VIN stands for, is voltage in. So that's going to be our feed to that. Now we'll also be sending power to our fuel pump switch. So without this power switch on, this fuel pump switch will do absolutely nothing if turned on. Once the switch is turned on, we will be sending 12 volts to the positive side of the relay coil. The other side being already connected to ground will immediately energize the coil and closing the circuit to energize the fuel pump. We'll go ahead and talk about the ground real quick. So our ground signal comes in and it'll be directly connected to the transistors, the switches, the ground, as well as the ground side of the relay and the ground side of the pump. So we are connecting our ground circuit to the collectors of our transistors. We are connected to one side of each one of our momentary switches. Doesn't matter which side, just any side will do. We then connect to the ground side of our Arduino. You do have 3 pins for ground. It does not matter which one you connect to. You can connect to any of the 3. It's all on the same circuit, so it does not matter. We then come over and you see we're connected to the ground side of our relays coil and then also the ground side of our fuel pump. So a very simple layout of our ground circuit. So we're going to move now into what might be considered a little more of the complex areas that deal with that are dealing more along the lines with circuits. That we're dealing more along the lines with circuits, the PWMs and resistors. The first thing we'll talk about is this one here being the 5 volt feed pull-up resistors for pins D2, D4, and D7. So this is what we were talking about with the 3 10K ohm resistors you'll need. And what that's for is when you're using the input pull-up, depending on how you're running that. In this case, we're sending a ground signal to pull the voltage down on 2, 4, and 7 to trigger our actions to kick off. When they're not being pressed, what's happening is you can get what's called a floating or sweeping signal on these pins, which it means that the voltage on these pins see neither 0 nor 5. However, if you were to have odd voltage spikes or decreases that can rapidly change the voltage on the board, they could momentarily see a voltage that is either 0 or 5 volts, triggering that input. So when we call up this as an input pull-up, we need to make sure that when the button is not pressed, it needs to see the complete opposite of what that completed circuit would show. And in this case, we want it to see ground when the button's pressed. When the button's not pressed, instead of a floating voltage, we want it to see 5 volts. And the way we accomplish that is by connecting each one of these circuits through a 10K resistor to our 5 volt line. So hopefully that makes it a little bit easier for you guys to understand why we're using those resistors there. So now that brings us to our 3 input pins from our momentary push buttons. So essentially all we're doing is getting ground on one side of our momentary button here, and then we're sending that ground signal up to our digital inputs where they're also going to be tied into that 10K resistor into the 5 volt line. That's just repeated for each switch, so a very simple circuit. So this is just a very simple on-off button that's just going to give it ground signal when pressed. So now we're going to go ahead and look at our 2 outputs that control our injector banks, which are digital pins 3 and 11 that send out the PWM pulses. So we're going to go ahead and look up here for those. We have 3 and 11. So these are going to control banks 1 and 2 respectively. So if we follow our diagram over, we're going to see that 3 connects over here to this 470 ohm resistor, which goes directly into the base pin of our transistor. The same thing is going to happen for bank 2 off pin 11. We're going to run directly to that base pin of our transistor via a 470 ohm resistor. So that's going to bring us to the very end here, which is going to be the output from the transistor to the banks themselves. So the emitter pins on both of our injectors are going to be connected directly to the ground signals of our injectors. So you see on bank 1 here, the emitter pin is connected to the ground side of injector 1 and 3, and the same thing for the emitter pin here is connected to the ground side of injector 2 and 4. So that covers the schematic we have here. So now that you guys know everything that's involved with putting one of these together, the coding process behind it, everything that goes into wiring it and building it out, the only thing left to do is to let you guys see it run. So I hope you guys enjoyed this video. I really enjoyed making it. So I hope you guys enjoyed what we're putting out there. There really was a lot of content to cover in this video, but if you notice anything I might have missed, might have skimmed over, something that just didn't make sense, reach out to us in the comments. We'll do our best to answer that for you. And like I said, I'm going to go ahead and put the link in the description below for our website where you can go and directly download the code we use today, as well as the circuit layout. And you can get it all for free. And while you're there, check out our merch store. If you see something you like, go ahead and buy it. And if you don't like them, go ahead and let me know. I need some input on that. I designed them all myself, and I need to know if they suck. But don't forget, like, comment, subscribe, do the necessary, and thanks for watching.